Section 3.2 is going to discuss rules for differentiation. And even though we're going to start using rules to calculate the derivatives, it still refers to the rate of change of a function. Whenever you get the derivative, it represents the slope of the tangent line at a particular point. So we're going to go through a few basic rules of differentiation and eventually start introducing more and more sophisticated rules for differentiation. But let's start out with the most basic one, and that is the derivative of a constant. So let's let f of x equal a constant. And let's think about the rate of change of that function. Well, I'll give you an example of such a graph, and that's over here. This is an example, f of x equals 3. Is that function changing a lot? No. In fact, if you were to calculate its tangent line and calculate the slope of that tangent line, what would the slope of the tangent line be? 0. All right, so back to our function then. The derivative of a constant function is 0. So f prime of x here would be 0. Derivative of a constant is 0. There's a couple other more basic definitions that I'll introduce. The one that's going to help out the most is the derivative of a polynomial function. So if f of x equals x to the n, then f prime of x is n times x to the n minus 1. And that's a real handy one. It's going to make your life in terms of calculating derivatives so much easier. Let's practice that with a couple examples. We'll start with problem number 6. Y equals x to the 12th. You could also write that as f of x equals x to the 12th. What's the derivative going to be here then? 12x to the 11th power. Wow, that's nice. That's really nice. Think about it this way. If you had to calculate that from the definition, limit as h approaches 0, that'd be x plus h to the 12th power minus x to the 12th power over h. Wow. Expanding that one, multiplying s plus h by itself 12 times, and then collecting all like terms, you'll be here a week from now. No thanks. So it's nice to have these souped up rules here to help us calculate derivatives. Another one that I should mention along with these two, and actually you're going to get a lot of these, is this. The derivative, let me write it down here. If you have, well, I don't want to write it. If you're going to differentiate a function that's being multiplied by a constant, so here's some new notation for you. The derivative with respect to x of a constant times f of x is the constant times the derivative. So constant times f prime of x. Basically, you can ignore the constant. You kind of pull it out, you take the derivative of f, and then you just multiply by the constant anyways. So that's kind of a nice little feature about differentiation. Constants don't really do a lot in terms of affecting the derivative. Let's add two more to this list. That is the derivative of the sine, d by dx of the sine of x, and d by dx of the cosine of x. And for these, I want to look back at the graphs for a second. So let's look at the graph of, say, the cosine. So here's the graph of the cosine. We can get rid of this. Remember the derivative measures the slope of the tangent line. Well, let's take a look at the slope of the tangent line at some particular points, like down here at around x equal pi. What's the slope of the tangent line going to be here? 0. Over here at pi over 2, the function is going to be increasing. And then up here, slope of the tangent line at x equals 0 is also going to be 0. And then down here at pi, the slope of the tangent line again is 0. So if you started thinking a little bit, you might be able to convince yourself that something that has a slope of a tangent line, it's going to be a function that's 0 at negative pi, it's 0 at 1, and it's 0 at pi, that function would be the sine function. The sine function is the derivative of the cosine function. Well, other way around. Well, actually, kind of both ways, really. Derivative of sine is cosine, and derivative of cosine is negative sine. So let me write those down. Derivative of sine is cosine. Derivative of cosine is negative sine. I think I might have been a little bit off in my graphical analysis, but these two are certainly spot on. It's annoying that there's this extra constant of a negative here. It'd be nice if derivative of cosine was sine. It's not. There's a negative there. But let's put those two together and work on a couple of problems like number 10 and then number 20. Number 10 is g of x is the fourth root of x. Oh, do I need to give you another differentiation rule to handle roots? There isn't one. But you can rewrite g of x, x to the 1/4 power. And now you can use your rules up above. The exponent comes out in front. So 1/4 x. What's going to be left in the exponent? Yeah. When you subtract 1, you're going to get a negative 3/4. Now in this class, this is fine. You can leave it like that. I have no issues with this. This is not an algebra class. I'm not worried about it. But were it an algebra class, I'd ask them to write it with positive exponents. And just for your own good, you should be able to, in a pinch, rewrite that as 4 times the fourth root of x cubed. So you should be comfortable with all that. Chances are, I'll be happy with it right here. But depending on the need, you might need to rewrite it. Let's take a look at problem number 20. You know, part of the reason for that used to go back to the fact that we didn't have calculators. Part of the reason. Because if you didn't rationalize something, it was a lot harder to do the division. Let's take a look at 1 over the square root of 2. If you wanted to do that long ways, it'd be 1.414, etc. into 1. And boy, dividing that out would be a royal pain if you had to do it by hand, right? But if you rationalize it and have square root of 2 over 2, then doing it by longhand, you're going to divide a 2 into 1.414, etc. And that's a lot easier. You can start doing that all, 07, 07, etc. That's not so bad. But we got calculators nowadays. So part of the reason for that is gone. But it still persists a lot. People are going to want you to rationalize denominators. I appreciate the question, though. I'm going to change 20 to an x. G of x is pi times the cosine of x. Let's find the derivative. G prime of x. Now here's what I was talking about a little bit ago. Pi is a constant. You can kind of ignore that part. So it's going to be pi times minus sine of x, or better yet, minus pi sine of x. There's your derivative. Wow, a lot nicer than having to do that with limits. Let's do a couple more to finish up with. I'm going to do problem number 28, and then I'll have you do problems 26 and 27 to finish up. So, do problem, rewrite, differentiate, and then simplify. So 4 little stages in each of these problems. For problem number 28, we have y equals pi over 3x squared. That's quantity squared. In order to use our rules for differentiation, you're going to have to rewrite this. So the first step might be to say, all right, that's pi over 9x squared. And be careful. It's not just the x that's getting squared, it's the 3 that's getting squared. If I wanted the x squared and just the x squared, how would I have written this differently? Yeah, I'd write it without parentheses, right? All right. So be careful that you square this. And I'll further rewrite that as pi over 9 times x to the negative second. Okay. Why did I do that? Well, now I've got a constant times some power of x. And I can differentiate that. So y prime or dy dx. Here's some more notation for you. dy by dx, the derivative of y with respect to x, is going to be pi over 9 times negative 2 times x to the negative third power. Ugh. Looks kind of messy. I'd like you to clean it up a little bit. And that's the last part, the simplification, where you could write that as minus 2 pi over 9 times x to the negative third. Or I guess one last step, you could drop that down into the denominator. Minus 2 pi over 9x cubed. Yes?
In the diff part, what did you, how did you know it's good for dy and dx?
Well, another notation for this I could have written it'd be y prime. It's just a different notation for the derivative. So the derivative came about from the right-hand side. You got a constant here, so I ignored the constant. I looked at that part. How do you differentiate x to the negative 2? The negative 2 multiplies out in front, and then subtract 1 from the exponent. So that's exactly what we did. The constant just stayed out in front. Let me write down 2 more problems here. Problem 27. Y equals 6 over 5x cubed. Oops, 5x cubed would be on the outside. And 26. Y equals 3 over 2x to the fourth. So what I want you to do is I want you to work both of these, rewrite them, differentiate them, and then simplify them. The simplifying is something that you want to work on because later on we're going to start using these derivatives as a small part of a bigger problem. So you want to get comfortable working with them and simplifying them. Oh, it's just, this is just a typo. Yeah, it's underneath the fraction bar. It's a -3 here. It's a +3 here. Because when it technically it's in the numerator here, and when you make the negative a positive, you're switching it down to the denominator. So yeah, it becomes positive there. Yeah, you could write it as -2x or -2 pi x to the negative third all divided by 9. That'd be fine. No, nothing wrong with that. Joseph, was that your question too?
No, mine was just to check the 2x is not supposed to be in parentheses for 26.
Correct. There's no parentheses here for 26. All right, so as far as the rewrite is concerned, that'd be 6 over 125x cubed, which you probably rewrite it again as 6 over 125 times x to the negative third power. Matt?
Was that parentheses there initially? Or did you
Yes. No. Parentheses were there initially.
Oh, okay.
What I don't understand is in the rewrite, x to the negative third. Are you putting that in the numerator?
Well, kind of the numerator. Well, see, I got it out of the denominator and I put it out by itself. Technically, this could be paired up with the numerator, but this is a constant. So I just want this x by itself so I can differentiate the x to the negative third power using our rules. So I want to leave this constant by itself. And why am I leaving the constant by itself? What's the derivative of a constant? Derivative of a constant is 0. So we can ignore that part. It's not going to affect our overall work here. I just need to find the derivative of x to the negative third. So the derivative of x to the negative third is -3 times x to the negative fourth. But that constant is still out in front. So that's 6 over 125 times -3 x to the negative fourth. Then, yes? I differentiated it. So the process of differentiation, you multiply by the exponent, so that's where the -3 came from, and then subtract 1 from the exponent. As far as simplifying this is concerned, that's -18 over 125x to the fourth. So I did two things. I combined these two, and I put this down in the denominator. Last but not least here, how should I rewrite problem number 26? Thank you. 3/2 x to the negative 4. So that's our rewrite. Let me use different notation again for our derivative. So that's y. I can write this as dy by dx. That's the derivative of y with respect to x. It means the same thing as y prime. And I know that you might feel a little overwhelmed. Like, oh my god, how come there's so many notations? Sorry, it's just what we use. You'll get pretty comfortable with it soon. If I differentiate this, I'm going to have 3/2 here. -4, x to what power? -5. These two will cancel, so I'll get -6, x to the -5th, or better yet, -6 over x to the 5th. Whew. Any wrap-up thoughts on those last three there? Okay, let's give you some homework and get you on your way. For homework, let's try 3 through 29. So that's section 3.2. We'll do more next time. 3 through 29. You have a test a week from today. I strongly suggest that you not get behind on the homework because the new material we cover on Tuesday is going to be on your test on Thursday. It's going to be tough to cover new material and catch up with the old material if you get behind. So stay ahead of the game. Have a great weekend. See ya. Yeah, I do got to take attendance.